So previously we saw that we can write a vector, let's call it t, in terms of components. These are t superscript I, so these are the contravariant components, and natural basis vectors, ei. Okay, so these are contravariant components, and these are the natural basis vectors. And we saw that these ei's were defined by dr by dxi, where xi is the ith coordinate in our n-dimensional coordinate system. So we saw that these natural basis vectors are tangential to the coordinate curves. So now let's ask the question, if we know our vector t, so if we have some vector t, and we choose a coordinate system, that means we've chosen a set of natural basis vectors. So let's choose a coordinate system. x1, x2, for example. Then how do we get the components in that coordinate system? Okay, so how do we get the components if we know a vector and the coordinate system? So for an orthogonal system, this is easy. So for an orthogonal system, we have that basis vectors, natural basis vectors, ei dot ej, so the dot product of two of the natural basis vectors, equals the modulus squared delta ij. Okay, which this is 1 if I equals j, and 0 otherwise. Okay, and we have this mod squared because these are not necessarily unit vectors, as we saw in the polar case previously. But with this, we can easily get this component. So if we have the vector t, then all we do is take the dot product with ei. Okay, and this equals, if we write what t is in terms of its component and vector form, this is tj, ej, dotted with ei. Let's use the blue. Ei. Okay, and just using this from above, we then know that this equals tj e I or j, it doesn't matter. Let's call it I squared delta ij. And this delta ij acts with the j to make this just ti mod ei squared. Okay, so ti is equal to t dot ei. So the vector that we know, the basis vector that we know, divided by the magnitude of the basis vector that we know. Okay, and this is just what we've known from school days. If we have a two-dimensional coordinate system, let's have it x and y, and some vector t, then the component of t in the x direction is just t cosine this angle, and that can be found by just taking t and dotting it with the unit vector I. Okay, that equals tx, the component in the x direction. Let's call it tx. Okay, so in this case, our natural basis vectors are unit vectors, so this denominator is just 1. Okay, so let's see what happens in a more general case where our coordinate system isn't orthogonal. So let's consider a more general case in which our coordinate system isn't orthogonal. This is x1, this is some x2, and we know that our natural basis vectors are tangential to the coordinate curves at these points. So this is E1, natural basis vector in the x1 direction, and the natural basis vector at this point for the x2 coordinate is shown here. So in this more general case, we have that EI dot EJ, and let's make these unit vectors. This is not equal to delta IJ. Okay, so we have to work harder now to get the components Ti if we know the vector and the basis. Okay, and knowing the basis just means choosing a coordinate system, okay, because the basis comes with the coordinate system. So what do we do in this case? How do we get the components Ti? Well, this is where we now start to think about different types of basis vectors. And for any set EI of natural basis vectors, I equals 1 up to n, there exists a dual set or reciprocal. Okay, different people use different words. Reciprocal basis, and we call this E superscript I to distinguish it from this. And it again is n-dimensional. Okay, and these dual basis vectors have the property that EI, a dual basis vector, dotted with a natural basis vector, lowercase j, subscript j, equals delta ij. Okay, and this delta ij, it doesn't matter where we write the superscript and subscripts. We can write this as delta ij or delta ij. Okay, we'll see this later. Okay, but and every set of n-dimensional basis vectors, natural basis vectors, has this dual set. Okay, and if you've done some quantum mechanics, okay, this is basically a linear algebra problem, but if you've done some quantum mechanics, then you can think about these guys as your bras and these as your kets. Okay, and you'll have an expression ij is delta ij, something like this. Okay, so it's analogous, if not exactly the same. So to find the components in this case, this more general case, let's take the vector t and let's act with it by taking the dot product with one of the dual basis vectors, EI. So this is equal to the t, the vector t, which is t, and let's use the index j, E natural basis vector j, dotted with the dual basis vector I. Okay, and we know that from the line above that this, okay, it doesn't matter which order these are in. Okay, so we can swap the order. This dot product is equal to a Kronecker delta. So this is just T, J, delta, I, J. Okay, which just equals Ti. Okay, so in our case we found that Ti is equal to the vector dotted with the dual basis vector. Okay, so this is the general result. And for an orthogonal coordinate system, we find that our dual basis vector is equivalent to the natural basis vector. Okay, so for an orthogonal system, we have that a natural basis vector is equal to its dual. Okay. But this is not true in general. Okay. And we'll see that these dual basis vectors can be used with the covariant component to provide a different representation of our vector. But let's think about what these dual vectors actually are. So let me rub this out. And let's look at this a bit more closely. And it's telling us that, it's telling us that the dual basis vector is orthogonal to all of the other natural basis vectors. Okay, so the dual basis vector for coordinate I is orthogonal to the natural basis vectors of all the other coordinates. So if we think about our coordinate curves, let's have this as the coordinate curve for x1 and the coordinate curve for x2, and let's have a coordinate curve for x3. Okay, and the coordinate curve is the line that we draw through space if we vary just one of the coordinates, keeping all the others constant. So we've seen that our natural basis vectors are tangential to the coordinate curves. So the coordinate curve for x1 is here, and our natural basis vector is e1. Our natural basis vector for the second coordinate, e2, and our natural basis vector for the third coordinate is e3. This is telling us that for example, for x3, the third dual basis vector, e3, is orthogonal to the natural basis vector for 1 and 2. So e3 is perpendicular to e1 and e2. This is the dual basis, e3. Okay, and it's perpendicular to the coordinate surface that is drawn out by e1 and e2. So there's some surface that the vectors e2 subscript and e1 subscript live in. And this e3, this dual basis vector, is perpendicular to this coordinate surface. Okay, so here's our surface. And similarly with e2 and e1. Okay, so e2, the dual basis vector for the second coordinate, is perpendicular to both e1 and e3. Okay, so there's some sort of coordinate surface that both of those vectors are in, and e3 points perpendicular to it. Sorry, e2. So now that we have the dual vectors at hand, we can write our vector in a different form. Instead of with the contravariant component and the natural basis vector, we can write it with a covariant component, t subscript I, times the dual basis vector. Okay, and that's what we introduced in the last section. Okay, so these are covariant components. And we saw that those ones were formed when we shone our torch perpendicular to the axis that we wanted the component along. Okay, and these are our dual basis vectors. And these are our contravariant components and our natural basis vectors. Okay, so what if we want to find one component in terms of the other? So let's think about the right-hand side, T, I, E, I. And let's take the dot product with one of the natural basis vectors, ej. So that's this. And on the left hand side, this equals ti ei, that's just here, dot product with ej. Okay, and we know that this, from the definition of our dual vectors, is delta ij. So this thing on the left hand side is ti delta ij, okay, which is just equal to t subscript j. And this equals this thing, ti ei dot ej. Okay, so if we know our basis vectors, our natural basis vectors, and a contravariant component, then we can work out the covariant component. Okay, and we'll look now at how these all transform under a coordinate transformation. And that will be us soon wrapped up with vectors and ready to start with tensors. So if we focus on this representation of our vector t subscript I, so this is the covariant component with the dual basis vector, then we can write this equivalently in a different coordinate system, a barred coordinate system. So we have ti bar and dual basis vectors for a barred coordinate system. Okay, so this system is x1 to xn, and this system is x bar 1 to x bar n. Okay, and we want to know how the ei bar and the ei are related. So how do the dual basis vectors transform between the coordinate systems, and how do the components transform between the two coordinate systems? So remember, our dual vectors were defined by let's think about the barred one, ei dot with ej bar natural basis vector equals delta ij. Maybe we have the I on the top, but it doesn't matter. Now, let's assume we can write ei bar in terms of ei with some matrix that multiplies it, a, I, k, and we need a k here. Okay. So let's just assume this, and we want to determine what this a, I, k needs to be for this to be true. So let's substitute this into the line above, and we find that a, I, k, e, k dot e bar j equals delta I, j. And we know what e, j bar is in terms of ej. It's given by e, j without a bar and some Jacobian matrix element dx by dx, and the bar is on the bottom here, and we need a j here, and forgive me, I need to have a different index here, k. So we substitute this in here, and we have a, I, k, e, k, and e, j bar now becomes dx, and I've already got a k, so I'm going to change this k again, so let me call it L. So dxL by dx bar j E L equals delta I j. And there's a dot here. Okay, so let's take out the non-vector quantities. We've got a, I, k, delta xl by delta dx bar j. ek dot el equals delta ij. Now we know that this is delta KL. So we find that AIK dx, and L becomes K, K by dx bar j equals delta ij. So at this point we can see that we can get our AIK, which is what we want to find, by just trying to get this to the right hand side. So to do that, let's multiply both sides by a dx bar j by dx m, dx bar j by a dx m, and we sum over j now, so this is a chain rule, so this becomes AIK dxk by dxm equals, I and j must be the same, so this is dx bar I by dxm. And we know that the partial derivative of one coordinate with respect to the other, so they're both unbarred, so this will give us a delta km. Okay, so let me bring this up here. Apologies. So we find that AIK delta km equals dx bar I by dxm, which means that AIM equals dx bar I by dxm. So this matrix that takes us from one dual basis vector, that in the unbarred system, to the one in the barred system, is given by this, and this, I hope you will see, is just an element of your Jacobian matrix. Okay, this is actually the J bar, so this is the inverse Jacobian matrix. So let me rub out and just clean this up a bit. So what we're saying is that if we have our dual basis vector in one coordinate system, we can find it in the barred coordinate system by just having a matrix element of our Jacobian matrix as such. And this is a key equation, and this is an element of our J bar matrix. Okay, so as we saw in the case of the contravariant components with the natural basis vectors, here, if we change a coordinate system, the transformation from the dual basis vectors, from the unbarred one to the barred one, must be inverse to the transformation undergone by the components. Okay, so they do the inverse of each other to keep the vector t invariant. Okay, so we'll find that, and you'll see it in your notes, it's just using the chain rule again and concepts we've already looked at, that the covariant components Ti in the barred system, they transform from the unbarred system with a Jacobian matrix element that involves an I here, oops, this should be a J here, and we have a bar on the bottom. So this involves the matrix J, which is the inverse of this. Okay, so if we look at Ti bar multiplied by Ei bar, we see we get a T and an E, and then two matrix elements, and it's the matrix J and J bar, and they're inverses, so they their effects are effectively cancelled. Okay, so our vector remains invariant. So let me summarize what we found for vectors on one last board, and then we move on to tensors.